So here's where we're going to use centroids in the immediate future, and this is the main way we're going to use it, maybe the only way, definitely the main way. I think it's the only way. We're going to use it in statics this semester. Again, you will be using this in other courses in the future if you go the path, but this is a particular application of centroid in statics. We have something called distributed loads. We also call them, if they're straight across rectangles, we'll call them uniform loads or uniformly distributed loads or line loads. And what they are is they are not discrete points. Like, think about like the self-weight of this beam. I mean, if this beam's made out of concrete, I mean, you could say there's a point load right in the middle, right? And sure, that could be at the center of mass. And I think you're seeing where we're going with that. Isn't that the centroid of it were a rectangle? Yeah, it was. All right, well, this is a triangle. So imagine this, instead of being, maybe the beam's getting wider linearly as we're going along, so the weight's getting bigger and bigger and bigger. Or maybe this isn't the self-weight. Maybe this is like, we've got one book stacked for the first foot, and then 2 books on the second foot, and 3 books on the third foot, 4 books on the fourth foot. You see how it goes. And so the weight that the beam is being loaded with here is increasing. And it's 150 pounds per foot when you get to the tall end. W, this italicized W, is often what we use to denote uniform loading or distributed loading. And so this one starts at 0 and goes to 150. So if you went into the middle here, it'd be 75. Right? So if we want to turn this into a resultant force, because we can't really do a whole lot of statics with a distributed load, what do? The resultant is the area under the curve, so the area of this triangle, which is 1/2 base times height. So 1/2 of 30 feet times 150 pounds per foot. Look at that, the math, the units even work. Okay, we're going to get 2,250 pounds, and where does it act? Yeah, you knew it. It acts at the centroid of the triangle. Okay, this happens to be a triangle. They don't all happen to be triangles. If you have that uniform load, the rectangular load, like we were talking about earlier, of course it would be right in the middle. So like that self-weight of that beam, you said you knew that you could replace it with that load right in the middle. Now that makes sense. Why? Because it's actually at the centroid of the load area. What about this one though? I don't recognize that shape. I don't think you could find one like this. So, I mean, is that a loss? I don't know. I mean, what if we subdivide it and make it up into some more realistic shapes? Like perhaps a triangle and a rectangle. So we got a triangle up here now and a rectangle down here. And we can treat them separately and add their effects together. So if we want to, we can turn it into 2 resultant forces to take care of this distributed loading. So now we've got that rectangular uniform loading down here. That's going to be of an intensity W1, and it's going for a length of L1 plus L2. And then the triangular load is now, it's starting not really at W1, is it, if we're considering this a triangle? It's starting at 0, and then it's going up to a value of W2 minus W1. The height right here is W2 minus W1. That is one of the biggest mistakes students make, is they'll do 1/2 the base times the W2 height. And that is not this triangle. That's a triangle that goes way over here like that. And that's a much different triangle. You've got to subdivide this up into the right shapes underneath it, that together, when you piece them back together, they make an exact match of the original loading. Otherwise, you're going to double up load, and that's no good. Okay, so our resultant of our uniform rectangular load is just going to be the area of a rectangle, so base times height. So L1 plus L2 is the base, and then W1 is the height. So that would be your rectangle. So L1 and L2 might be in meters or feet or something, and the W1 would be in load per meter or load per foot. So it might be in kips per foot or pounds per foot or something like that. So the FR, the resultant force, is going to be like in pounds or in kips or in kilonewtons or whatever it is, right? And where is it acting? It's acting at the centroid of the rectangle, which is halfway across. The horizontal location of the centroid. The vertical is not important because the force acts through this line of action. So you don't need to find the vertical location of the centroid, just the horizontal for this particular application. And that's going to be at L1 plus L2 divided by 2, right? So that's easy. And then the triangle over here, its resultant would be 1/2 base times height. So 1/2, and in this case, L2 times the height of W2 minus W1. Remember, that's your height of your triangle. That's that side right there. And where does the resultant act? At 1/3 from the tall end of a right triangle, or 2/3 from the pointy end of the right triangle. And that's what we're dimensioning here. And the pointy end starts here at this distance of L1 away. So if I'm going all the way from this side, I do L1 plus 2/3 of L2. 2/3 of L2 is that 2/3 the length from the pointy end of the triangle. Boom. So that's going to be, if you wanted to turn this into an equivalent system, you would have 2 resultant forces here. Now, you already know that what if you want to turn it into just one? You could do that. You could find the resultant by adding these 2 effects together and then saying, well, where would I place that such that the moment would be the same? It would be somewhere over in this region right here. It's the weighted average, but that was something that you did when you did the moment equivalent force system calculations in the previous work. All right, one final note here. We are not doing center of gravity and center of mass and center of volumes. They all can be done. They're all basically the same calculations. They're extremely similar calculations. So you can do it on your own. You might have done some center of gravity calculations in previous classes, but we're not doing anything with volumes in here or center of mass or center of gravity. What you learn here with centroid will get you to the rest of that stuff. Thanks for watching.